Hello and welcome to Mr. Tompkins EdTech and a brand new series of videos aimed at helping you prepare for your GCSE mathematics exams. In this series I'll be giving a complete walkthrough of the GCSE mathematics practice papers to help you prepare for your exams this summer. Now there are not so many of these and you don't want to squander them, so make sure you try the paper yourself first before you look at these solutions. This particular paper is Edexcel 2021, paper 3, higher tier. Check the front cover of your paper to make sure it's the same one. If it's not, have a look through the playlist linked above, which includes all the GCSE maths video walkthroughs I've recorded so far. I'm busy recording all of the GCSE practice papers, so if the one you're looking for isn't there already, why not subscribe by clicking the big red button below and check back in a few days. Don't forget to click on the bell so that you'll get a notification when I upload the next paper. I'll put timestamps in the description below, so you can choose to watch the whole thing through, or you can click on the timestamp and jump to the particular question you need help with. If you have a question, check the comments below, as someone else might have already asked the same thing. If it's a new question, leave it in the comments and I will try and answer all of them as soon as I can. Don't forget to mention which question on the paper you're referring to and try and be as specific as possible. Finally, if this video helps you with your revision, please give it a thumbs up. It will really help me out, and why not share the link with your friends, because they might need a helping hand too. Okay, let's get into it. Question 1. The scatter graph shows information about the volume of traffic and the carbon monoxide level at a point on a road each day for 22 days. Okay, we can see on the graph we've got volume of traffic going across the bottom, and that's in number of cars, and we've got carbon monoxide level in milligrams per cubic meter going up the side. Now it says here that one point is an outlier. Write down the coordinates of this point. Well, an outlier is a point that doesn't kind of match the rest of the trend, and you can see that most of the points are kind of in this band running up the center of your data here, but we've got this one all the way over here. This one is the outlier, isn't it? So what point is that? That is 100, 18. So I'm going to write that down. 100, 18. For another day, 370 cars passed a point on the road. Estimate the carbon monoxide level for this day. Now, in order to do an estimation from a scatter graph, we need first to have a line of best fit. Now, I said that the trend line was kind of up here, wasn't it? So if I put a ruler kind of halfway through my data, so I've got half the points on one side and half on the other, running in that general direction, then that's going to be our line of best fit. Now, this is a little bit of a esoteric activity. It doesn't always have to be perfect, but it should just be kind of running generally through your data. And, you know, there'll be a certain tolerance that you can have. If yours is a little bit taller, a little bit less tall, it's not going to matter a great deal, as long as it's kind of vaguely going up in that direction. Okay, and now we can use that line of best fit to do our estimation. So 370 cars along the bottom axis takes us to, well, we've got 10 divisions between 300 and 400, so each one's going to be worth 10. So 370 is going to be 7 little squares up from 300. So about there. Let's read up to the graph. Then we get to the graph, change directions, go in the other direction till we hit the other axes. Right, and you can see it's pointing there, a little bit below 14. Now on this scale, we've got 5 divisions between 12 and 14. So we've got 5 divisions spanning a distance of 2. So each one's going to be 2/5 or 0.4, isn't it? So it's going to be 12, 12.4, 12.8, 3.2. So that one's going to be 3.6 then, isn't it? Or 13.6, I should say. So that one's going to be 13.6 milligrams per cubic meter. Now you'll be marked against your line of best fit. So if you've drawn your line of best fit slightly differently to mine, then whatever your number should be when you do the same thing, if you read up from 370 and across, that is what you'll get marked against. Okay, so don't worry if you don't get exactly the same as me, but as long as you've read the scales properly and you've kind of bounced off your line of best fit and along the other direction, you'll be fine, you'll get the marks. Alfie says, because there is an outlier, there is no correlation. Is Alfie correct? You must give a reason for your answer. Now, I don't think Alfie is correct. I think you can have outliers and still have correlation. So I'm going to say no. Now, there's 101 reasons why you might get an outlier. It might just be an error in recording the data. So someone might have actually like put 13 down instead of 3, you know, or something like that. Could just be an error that way. Or it could just be that you've got one event that just doesn't fit the pattern, you know. So it might have been like a really windy day that day, or a really still day. So I think it was high, wasn't it? So it was too high compared to the number of cars. So it might have just been a really still day with no wind, and you know, everything was just sitting in one place. So there might be 101 reasons why you might get an outlier. So just because you've got one doesn't mean you don't have correlation. All the other points fit in a nice neat pattern. So I'm going to go with that. So I'm going to say no. Outliers can happen due to errors in data capture or simply individual cases that don't fit the overall pattern. All the other points clearly show correlation. So that's what I'm going to say. Okay, so no, outliers can happen due to errors in data capture or simply individual cases that don't fit the overall pattern. All the other points clearly show correlation. Question 2. Natalie makes potato cakes in a restaurant. She mixes potato, cheese and onion so that the weight of the potato to the weight of the cheese to the weight of the onion is in a ratio of 9 to 2 to 1. Natalie needs to make 6,000 grams of potato cakes. Cheese costs £2.25 for 175 grams. Work out the cost of cheese she needs to make 6,000 grams of potato cakes. Okay, so this is got quite a few steps to it, isn't it? I think the first step we need to do is this divide in a ratio step. So we've got 6,000 grams of potato cakes that we need to make, and this is the ratio of the weights of their ingredients, isn't it? So if I divide 600 grams in a ratio of 9 to 2 to 1, then I'll know how much of each ingredient I need. Therefore, I'll know how much cheese I need, and therefore I can work out the cost of that cheese. Okay. So step 1, let's do that division then. So if I've got a ratio of 9 to 2 to 1, then I've got 9 plus 2 plus 1 parts, haven't I, or shares. So that's 12 shares altogether. Okay, so then if we then divide our 6,000 grams into those 12 shares, 6,000 divided by 12, what's that? Reaches for calculator. 6,000 divided by 12, that comes to 500. 500 grams. So that means one share is worth 500 grams. So then if I take my original ratio of 9 to 2 to 1 and I scale that up by a factor of 500, that means I'm going to have 9 lots of 500. That's 4,500 grams of potatoes, 1,000 grams of cheese, and 500 grams of onion. Okay. So how much cheese do I need? I need 1,000, because that was the 2 was the 1,000. That was the cheesy column, wasn't it? So I need 1,000 grams of cheese. Require 1,000 grams of cheese. Okay, so then I know that cheese costs £2.25 for 175 grams. So to make 1,000 grams, or for 1,000 grams of cheese then, so the cost of cheese. So anyway, so if I take 1,000, which is the amount of cheese I need, and divide it by 175, that should tell me how many packs of 175 gram cheese I need, and then I can multiply that by the cost of cheese, which is £2.25 then, isn't it? So what's 1,000 divided by 175 times by 2.25? That comes out to be £12. It's a recurring decimal, but it's still going to round off to, still going to round up, isn't it? It's going to be £12.86. Question 3a, write 4.5 times 10 to the 5 as an ordinary number. Okay, so if I got 4.5 and I'm going to times it through by 10 to the power 5, that's equivalent of moving the decimal point 5 jumps to the right, isn't it? So it's going to go 1, 2, 3, 4, 5 jumps. So our decimal point is going to end up over here, which means I'd need to kind of fill in some extra zeros along the way in order to, that I can drop the decimal point there. So that gives me 450,000. The other way of thinking about it is 10 to the 5 is hundreds of thousands, so it kind of just translates your number into hundreds of thousands. Right, 0.007 in standard form. The way I do this, I just do it 7 times 10, and then I count the number of zeros I can see. So I can see 1, 2, 3 there, so it's going to be 10 to the minus 3. Okay, so 7 times 10 to the minus 3. Work out 4.2 times 10 to the 3 plus 5.3 times 10 to the 2. Give your answer in standard form. That's really easy with a calculator. Just have to type it in. So 4.2. You've got this exponent key down here with times 10 to the x written on it. So just press that, and then the only other thing you need to put in it is the power, which is 3. Okay, so 4.2 times 10 to the 3 plus 5.3. Type in the manticipart. Press that button down there, times 10 to the x, and then tap in the power, which is 2. Okay, so what's that equal to? That equals to 4730, but remember they want it in standard form, don't they? Okay, so I'm going to have to rewrite that as the manticipart as a number between 1 and 10. It's going to become 4.73. What's the power of 10? Well, the decimal point would start here. It's going to end up going 3 jumps to the left. So that is going to be times 10 to the 3 then, isn't it? So 4.73 times 10 to the 3. Question 4. A water tank is empty. Anil needs to fill the tank with 2,400 litres of water. Company A supplies water at a rate of 8 litres in 1 minute and 40 seconds. Company B supplies water at a rate of 2.2 gallons per minute. 1 gallon is 4.54 litres. Company A would take more time to fill the tank than Company B would take to fill the tank. How much more time? Give your answer in minutes, correct to the nearest minute. Okay. So we're going to have to work out how much time each company takes, and then we're going to have to compare them. I'll take one away from the other and see what that is. Okay. So let's take Company A to start with. Company A. What do we know about Company A? Well, they're both delivering the same amount of water. It's 2,400 litres, isn't it? Now, Company A delivers water at the rate of 8 litres in 1 minute and 40 seconds. Okay? So what we need to do is to work out how many lots of 8 litres we have in 2,400 litres, and then multiply that by the time it takes to deliver it. Okay, now I don't like the fact that I've got mixed units there of minutes and 40 seconds. So I'm going to say that I'm going to rewrite it. I'm going to say that 1 minute and 40 seconds. I'm just going to write it in minutes. So that is 1 minute and what fraction of a minute? It's 40/60ths, isn't it? 40/60ths of a minute, because there are 60 seconds in a minute and I've got 40 of them. That's the same thing as 1 2/3. So I've got 1 2/3 of a minute. Okay, so Company A can deliver 8 litres in 1 2/3 of a minute. So if I take 2,400 divided by 8, that will tell me how many lots of 8 litres I need, and then multiply that by 1 2/3, it should give me the time, shouldn't it? So 2,400 over 8 times 1 2/3. Okay, that comes to 500. That's a nice, neat number. So that takes 500 minutes. What about company B? Now, company B supplies 2.2 gallons per minute. Okay, and we've got a conversion here of gallons to litres. 1 gallon is 4.54 litres. For those you don't remember, back in the day. Anyway, so what we're going to have to do, so we're going to have to work out how many gallons we've got. So if we take 2,400 and we divide it by 4.54, that will tell me how many gallons I've got. I think I'm going to do that first. So 2,400 divided by 4.54, that comes to 528.6 gallons. Okay, now I'm going to leave that calculator value on my calculator, and then I'm going to go on and do the second part of the calculation. So now I know I've got 528.6 and a bit gallons. I need to take that, so time taken is going to be that 5286 and a bit divided by, well, we can deliver 2.2 gallons per minute. So if I divide that, if I find out how many lots of 2.2s fit in there, then I know how many minutes it's going to take then, don't I? So I just need to divide that number by 2.2. Okay, so that's 240.3 minutes, 240.28. I think I'll just round it off to 240.3 minutes at the moment. That's a decimal fraction there. Okay, so company A can deliver it in 500 minutes. Okay, and company B can do it significantly quicker at 240 and a bit minutes. Okay, how much more time does company A take then? So difference is going to be 500 minus 240.3. So 500 minus answer, that comes to 259.7, which I'm going to round up to the nearest minute. So that's 259.7, and that is equivalent to around about 260 minutes then to the nearest minute. Okay, 260 minutes. Question 5. The first 4 terms of a Fibonacci sequence are A, 2A, 3A, and 5A. The sum of the first 5 terms of this sequence is 228. Work out the value of A. Okay, so first up, we've only got 4 of the 5 terms here, so we're going to have to work out what this 5th term on the end is. Now, with a Fibonacci sequence, the previous 2 terms give you the next term, doesn't it? So like A plus 2A is 3A, 2A plus 3A is 5A, 3A and 5A is what? That is 8A, isn't it? So the 5th term is going to be 8A. Okay, so we know 8A is the 5th term. So what do all the terms add up to then? So the sum of 5 terms, that's going to be A plus 2A plus 3A plus 5A plus 8A. How many A's is that then? So that's 10, 15, 18, 19 A's. So that's 19A. And we know that that is equal to 228 because we were told it was. Okay, so we know that's 228. So then A is going to be 228 then. Well, if I divide both sides by 19, look. Now leaving me with A on its own. So then A is going to be 228 divided by 19. So what's that? 228 divided by 19. That comes out to be 12. Question 6. In the bag, there are only red counters, blue counters, green counters, and pink counters. A counter is going to be taken at random from the bag. The table shows the probabilities of taking a red counter or a blue counter. The probability of taking a green counter is 0.2 more than the probability of taking a pink counter. Complete the table. Okay. So what I'm going to do here is I don't know how many counters, what the probability of pink is, but I know that green is 0.2 more than that. So I'm going to do this algebraically. I'm going to say, well, let x be the probability of getting pink. Then I can write then green down relative to pink then, can't I? I can say that green is 0.2 more. So green is going to be x plus 0.2 then, isn't it? Okay. Now, and I also know the rule for completeness in probability. If these are the only possible outcomes, then the sum of all of those outcomes must be 1, must be certainty. So I know then that 0.05 plus 0.15 plus x plus 0.2 plus x, the 4 values going to add up to 1, aren't they? So I can form an equation in x that I can then go on to solve. Okay, so I've got 3 numbery bits and I've got 2 algebraic bits. So the x plus x, that's just 2x, isn't it? What do all the numbery bits add up to? 0.2 plus 0.15, that's 0.35, plus 0.05, that's 0.4, isn't it? So I get 2x plus 0.4 is equal to 1. Okay, subtracting 0.4 from both sides. That's going to leave me with 2x is equal to 0.6, and therefore then dividing both sides by 2, I'm going to get x is 0.3. Okay, so that means green must be 0.3. So that means that pink must be 0.3 and green must be 0.2 more. Well, that would make it 0.5 then, isn't it? And all the 4 numbers now add up to 1. On to part B, we can see there are 18 blue counters in the bag. Work out the total number of counters in the bag. Okay, so 18 represents 0.15 in terms of probability. So if we could scale that up, we should get the full amount then, shouldn't we? So if I take, I'm going to write my answer to be up here. If I take 18 and I divide it by 0.15 and then I times it by 1, I should get what fraction that is of 1 then, shouldn't I? So 18 divided by 0.15, well, times 1 isn't going to change it, is it? I'm just going to get 120. So there must have been 120 of them altogether. So there's 120 counters altogether. Question 7. The diagram shows a sector OPQR of a circle, center O and radius 8. OPR is a triangle. Work out the area of the shaded segment of PQR. Give your answer correct to 3 significant figures. Okay, so to work out the area of my segment, so the area of the segment, that is going to be equal to the area of the sector, which is like the part of the circle which it's from, minus the area of the triangle. Okay, so this segment here is going to be the area of the sector, so that's all of that minus the area of the triangle, and that's just going to leave you with the segment part, isn't it? Okay, so that's the general plan. So in order to do that, we're going to have to know what the area of the sector is and what the area of the triangle is. Okay, so let's work out the area of those two things. Area of sector, well, what fraction of a circle is this sector? That's a right angle in the middle, isn't it? So when you're working out the area of a sector, it's the angle in the center divided by 360 times pi r squared, which is the area of a circle, isn't it? Okay. Or you could quite easily see that was a quarter circle to start with. Okay, so I'm going to reduce that to 1/4 of pi times the radius, which is 8 squared. Okay, so what's that then? So that's 8 squared, which is 64, divided by 4, which is 16. That is equal to 16 pi. And I'm just going to leave it in terms of pi for now, just because it's easier to write down pi than it is to write down a really long decimal. And let's go on and work out the area of the triangle. Area of triangle. Now that's just half base times height, isn't it? Because it's a right angle triangle. I know the base, I know the height. So I can just use half base height, which is going to be half times 8 times 8 then, isn't it? So it's half of 64, which is 32. Okay, so then the area of the segment is going to be the area of the sector, which is 16 pi, minus the area of the triangle, which is 32. Okay, so now I can actually type pi in to get a precise answer. So 16 lots of pi minus 32, what's that? That's 18.265. Now the question states, give your answer correct to 3 significant figures. It's going to have to round this one off after the third significant figure, so it's going to be 18.26. Round it off, it's going to be 3, isn't it? 18.3. 18.3 centimeters squared. Question 8a, using the axes below, sketch a graph to represent the statement y is directly proportional to x. Okay, this is a very simple sketch. It's just going to be a straight line graph, okay, but passing through the origin. Must go through the origin for direct proportion. Okay, so just any straight line, doesn't really matter how steep it is. Okay, that would depend on your kind of coefficient of proportionality, but it must go through the origin. It must be a straight line. Okay, now using the axis below, sketch the graph to represent as the statement y is inversely proportional to x. So if y is directly proportional to 1 over x, then if you were going to replace that with a constant of proportionality, you'd get y equals k over x. And this type of equation falls into the family of reciprocal curves, doesn't it? Okay, and reciprocal curves are very distinct two-part graphs which look like this. Okay, so now we're only plotting this bit of it up here, so my graph is going to look something like this. Okay, so it's a curve which is approaching the axes but never touching them, isn't it? Okay, so something that looks like that. Question 9, on Monday 12 people took 5 hours to clean a number of cars. On Tuesday 15 people cleaned the same number of cars. Assume that all the people worked at the same rate. A, work out how many hours the 15 people took to clean the cars. Okay, now with these work rates, this is a kind of application of proportionality. What I like to do is, if I've got 12 people who took 5 hours, the first thing I want to do is work out kind of how many hours, people hours it takes to do the work. So like the total sum of all the work. So if you times 12 by 5, you're going to get 60, which means that there's 60 hours worth of work to be done by somebody. Okay, so then if you take that 60 hours and divide it by 12 people, they each get 5 hours each. Okay, so but if you've got more people working on it, they're going to get through that work in less time, aren't they? So if I take that 60 hours worth of work and I divide it out amongst 15 people, then you can see that each are going to get 4 hours worth of work each, and overall the task is going to take 4 hours then, isn't it? So 4 hours. Now part B says the assumption is wrong. How might this affect the time taken for the 15 people to clean the cars? So what we're saying here is then that each person is not putting the same amount of effort in. So some people are working really hard, some people not so hard. Now it's hard to tell from the question whether or not the 15 people who are going to be washing the cars are working harder or not as hard as the 5 people who washed it the day before. So how might it affect the time? I think what could happen, the time taken could go either up or down, or stay the same? We don't know, do we? If they are working harder, stroke faster, it will take less time. If they are working slower, it will take more time. Question 10. The diagram shows two right angled triangles, ACB and DEB. AD is 9, DE is 2, and DB is 6. Work out the length of CB. Give your answer to correct to 2 decimal places. Now, it doesn't say it here, but this is a classic similar triangles question. So be on the lookout of this shape. The other one they like is kind of like the bow tie one, like this, where you've got two lines parallel to each other, and then lines between them crossing over, forming two triangles. So this one and this one are similar, and in this case you've got two triangles, one on top of each other. You've got this triangle here which sits on top of this triangle here, okay, and those two triangles are going to be similar as well. Okay, so it's a problem involving similar triangles. So we can use the fact that in similar triangles sides are always in the same ratio to help us find missing sides that we might need for this problem. So let's have a look at what they've given us. They've given us AD and told us that is 9 centimeters. So from A to D is 9 centimeters. From D to E is 2 centimeters. And from DB and DB, D to B is 6 centimeters. Okay, so that should be enough then to work everything out. Calculate CB. So what do I need to find? I need to find this length here. Okay, and that's it. So that's all I need to know. That's all I need to find. Okay, so when we're looking at similar triangles, the first thing we need is a pair of sides that go together, so that we can work out what the ratio is between the two triangles, or how much bigger, or the scale factor, I suppose is another way of saying it. Now if you look here, this one here, this side here, is going to be matching with this side of the larger triangle, isn't it? Okay, because you've got these two triangles sitting on each other. You've got triangle BDE sitting on top of BAC. Okay, so that 6 from DB is going to match up with the length A to B, which is 9 plus 6. It's going to be 15 altogether. So the distance of A down to B there, that is a distance of 9 plus 6. That's going to be a distance of 15. Okay, so then the smaller triangle is 6, the larger one is 15. So then the scale factor between the matching triangles is going to be 15 over 6 then, isn't it? Okay, which cancels down to, what's that, 5 over 2? Okay, so it's 5 over 2. I'm just going to leave it like that as a fraction. It's kind of handy that way. So calculate length of CB. Now to know CB, I could use EB and that scale factor to find it, but I don't know EB. But could I find it? I think if I use Pythagoras theorem in that small triangle DEB, I could find it, couldn't I? Okay, so in triangle DEB, I know this is 6 and this is 2. So in triangle DEB, we can use Pythagoras theorem. Which says the square on the hypotenuse, c squared, equals the sum of the squares of the other two sides. C squared equals a squared plus b squared. So rearranging that for our shorter side, we're going to get a squared equals c squared minus b squared, isn't it? In other words, it's going to be 6 squared minus 2 squared, which is what? So 36 minus 4 then, isn't it? It's going to be 32 then. And that means that a itself is going to be the root of 32. Okay, so then if that's the root of 32 there, which isn't a nice number, so I'm just going to leave it as the root of 32 for now, then my side BC, So then BC is going to be the scale factor 5/2 multiplied by the side of BE, which we found earlier, which is root 32. So what's 5/2 of root 32 then? 5/2 of root 32, that comes out to be 10 root 2, or to 2 decimal places, that's going to be 14.14 then, isn't it? So that's equal to 14.14. Always a good idea to imagine that number in your triangle. So if from here to here was 14 centimeters, that look about right? We know that the longer one was 15, and that's the hypotenuse. This one's going to be a little bit shorter, isn't it? Yeah, I think that looks okay there. So I'm happy with my answer, 14.14. Question 11, Freya writes down the value of x correct to 1 decimal place. She writes x equals 6.4. Complete the error interval for x. Okay, so for an error interval questions, I like to draw a number line and put on the value they've given us, which is 6.4. I'm going to mark that on the scale, 6.4. Now this was correct to 1 decimal place. So 1 decimal place above 6.4 on my scale is going to go up to 6.5. And 1 below would go down to 6.3. And so the numbers that round to 6.4 are going to be the numbers halfway between those numbers or closer. Okay, so it's going to be these ones, isn't it? This region here rounds to 6.4. So what are the numbers that are halfway between 6.3 and 6.4? That's going to be 6.35. That's my lower bound then, isn't it? And halfway between 6.4 and 6.5 is 6.45. Okay, I think that should have said a bit of a printing error there. That should be less than or equal to there. Okay, so it should be less. X should be greater than or equal to my lower bound, which is 6.35, then, isn't it? And then x should be less than my upper bound, which is 6.45. Question 12. Ax to the power of 6 all raised to the power of 1 over n is equal to 7x to the 3. Work out the value of a and the value of n. Okay. So I think what I'm going to do is I'm just going to take this more complicated side and I'm going to see if I can make it look more like the side on the 7x cubed. Okay, and then I can compare it a little bit better. So it's equal to ax to the 6 all raised to the power of 1 over n, isn't it? Okay. Now, when you've got an index of an index like this, you have to apply the index to both things inside the bracket like that, so it distributes over multiplication. So what I'm going to get is I'm going to get a to the power of 1 over n, x to the power of 6 over n. Okay? And that is equal to the right hand side, which is 7x cubed. Okay? Now, if these two things are equal, then both parts of them need to be equal. That means that this part needs to be equal to that, and it means that this part over here must be equal to that. Okay? So I'm going to use that to form two equations. I'm going to say a to the power of 1 over n must be equal to 7. And I'm going to say that 6 over n must be equal to 3. Okay? Now that second one looks easier to solve to me. Multiplying both sides through by n, I'm going to get 6 is equal to 3n. And then dividing both sides by 3, I'm going to get n is equal to 2. Okay? So once I know that, I can then sub it into the other half, and I can say, well, a to the power of a half is equal to 7. So then, to get a then, I'm going to have to kind of square both sides, aren't I? So if I square that and square that, I'm going to get a is equal to 7 squared is equal to 49. Okay? So that means a is 49 and n is 2. Question 13. A pattern is made from 4 identical rectangles. The sides of the rectangles are parallel to the axes. Point A has coordinates 3, 4. Point B is coordinates 11, 20. Point C is marked on the diagram. Work out the coordinates of C. You must show all your working. Now I think what I'm going to do is I'm just going to define my length and width of this rectangle algebraically, which I'm going to call L and W. Okay? And then what I'm going to do is I'm going to compare it to the difference in the coordinates that we've got here for A and B in both directions. So we can then compare how many rectangles we've got and then how, and the distance between them to work out what L and W actually are. Okay? Let's take the distance in the x direction first. So in the x direction, so the difference in coordinates is going to be, well, the x coordinate of B is 11 and the x coordinate of A is 3, isn't it? So that's equal to 8. But what does it mean in terms of the diagram over here? If you think about it, then I need to go 1L from here to here, then 1L from here to here, but I need to come back 1W, okay, to get to that coordinate there. So that difference is going to be an L plus an L minus a W in the direction of x. So 2L minus W is equal to 8. Okay? Now in the direction of y, in the y direction, the difference in the coordinates in this direction is the difference between 20 and 4, isn't it? So 20 minus 4, and that's equal to 16. Okay, but what's equal to 16? If you have a look at going upwards, then, so to go from A to B in the up direction, then I've got a W and then a L and then another L. So it's 2L plus W in that direction. Okay, so this should be equal to 2L plus W, and then that is equal to 16. Okay, so what I've got here is a case of simultaneous linear equations, which I should be able to go on and solve. Okay, now if I take equation 1 and I add on equation 2, that should eliminate the W, shouldn't it? So if you think about 2L minus W plus 2L plus W, the W is going to disappear, and I'm going to get 4L is equal to 8 plus 16, that is 24. That gives me a value of L of 6. Okay, so it's 6 in this direction. What does that make W then? So substitute L equals 6 into one of my original equations. Let's pick equation 1. So 2 lots of 6 minus W is equal to 8. So what does that make W then? 2 lots of 6 is 12. 12 take away 4 is 8. So W is equal to 4 then, isn't it? Okay. So W is equal to 4. Okay, so now I know that, I should be able to work out how far it is to C. So then the coordinates of C then, if you think about what C's coordinates are, if you start from A, which is at 3, and then I add on an L, one side of my rectangle, I'll be adding 6 on, won't I, to get to 9 in that direction. And then in the Y direction, if I start at A, which is at 4, I need to go up a width, don't I, a W. The width is 4, so 4 plus 4, that's going to take me to 8. So then the coordinates of C must be 9, 8. Does that look about right? I think it looks about right. 9, 8. C is 9, 8. Question 14. Olivia and Jessica have in total half as many sweets as Fran and Gary have in total. Fran and Gary share their sweets in a ratio of 2 to 3. Olivia and Jessica share their sweets in a ratio of 9 to 1. Fran got W sweets, Gary got X sweets, Olivia got Y sweets, Jessica got Z sweets. Find the simplest form of W to X to Y to Z. Oh my days, what's going on here? Right, okay, this is a bit complicated, isn't it? I think we're going to have to go through this a bit more slowly. Olivia and Jessica have in total half as many sweets as Fran and Gary have in total. So Olivia and Jessica have half as many as Fran and Gary. So what do we know? We know that Fran got W sweets and Gary got X sweets. So if I add W and X together, that is Fran and Gary's total, isn't it? Fran and Gary, that's those two. Olivia and Jessica had Y and Z, so if I add those together, I'm going to get Y plus Z. So those two together is that and that. I've got a feeling I'm just going to look at W to X to Y to Z and start putting some of this information in for me. So I know that Fran and Gary share their sweets in the ratio of 2 to 3. So Fran is W, so that's F. Gary is X. So Fran to Gary to Y is Olivia, and Z is J. So F to G to O to J, isn't it? Okay, and that's in the ratio W to X to Y to Z. So then Fran and Gary in the ratio of 2 to 3, so that's 2 to 3 there. And I know that Olivia and Jessica share their sweets in the ratio of 9 to 1, so that is 9 to 1. Okay, so altogether these two here, look, is 5 parts, and these two together is 10 parts. Now we're told that Olivia and Jessica have half as many sweets as Fran and Gary. So these 10 parts actually should be as half as many as the ones that Fran have. So if they've got 10 parts altogether, then really Fran and Gary must have 20 parts, mustn't they? They must have twice as many. They should have 20 parts altogether because they've got twice as many as Olivia and Jessica. Okay, so that means we need to scale up our Fran and Gary parts by a factor of 4. Okay, so that means if I multiply the ratio of 2 to 3, I'm going to get the ratio of 8 to 12. Now that should then match with the other two, because now we're in the ratio of 10 parts to 20 parts, which is twice as many for Fran and Gary as Olivia and Jessica got. Okay, so this then should be the complete ratio: Fran, Gary, Olivia, Jessica, 8, 12, 9 and 1. So finding its simplest form, W, X, Y and Z, I think that's it, isn't it? Okay, can I simplify it down? I can't, because I've got a 1 on the end there, so I'm not going to be able to simplify it any more than it already is. Okay, so that is the final form, 8 to 12 to 9 to 1. Okay. Question 15. The graph gives the volume of water in litres in a container at time t seconds after the water started to flow out of the container. So you can see the volume in litres is slowly decreasing over time. Okay, so the water is flowing out of the container. The rate at which it's flowing down, it starts off quite quick and then it's slowing down, isn't it? Because the gradient's getting less steep. Using the graph, work out an estimate for the rate at which the water is flowing out of the container when t is equal to 12. You must show your working. Well, t is equal to 12 on axes is here, look. So if I read up to the graph, then I can mark a point on the curve here. Basically, we want to find the we want to find the gradient of this curve at that point there, at the point where t is equal to 12. Now, finding the gradient of a straight line is easy enough. You just need to find 2 points in it and measure the change in y over the change in x. That's simple. But with a curve, it's a little bit more complicated because the gradient is constantly changing all the way down the line. So there aren't 2 points on it that you can use, because every point is at a different gradient as every other point. So in order to work out the gradient, we're going to have to draw an extra thing on our graph. We're going to have to draw a tangent to the curve. Now, a tangent to a curve is a point just touching the curve. Okay, so I think it's a bit of an art to get it right, and yours might look slightly different to mine, but I kind of look at the space either side and try and balance it out a little bit. Again, it's not an exact science. You are allowed a bit of wobble room in order to work it out. Okay, and then what I'm going to do then is work out change in y divided by change in x to find a gradient then. Okay, so change in y is the difference in this direction divided by the difference in this direction. Okay, so we can use the scale on the graph to help us. So change in y then, what's the height of that point? It's 7 units up from 10. Each one of those is about 1 unit. So I think the height of that line is 17. So the change in x is, well, it was 12 up to 29. 29 take away 12, I think that's a distance. So 29 take away 12. That is, what's that, 17? Oh, that's 17 as well. That's handy. So, gradient is equal to change in y divided by change in x. Okay, and that is going to be equal to, well, it's actually negative 17. Because we're going down, not going up, and positive 17. So that's going to give me a gradient of -1. Okay? So that's going to be -1 what? It's going to be -1 liters per second then, isn't it? At that point. So the gradient is -1, but the rate that the water is flowing out is just 1, isn't it? Because it's flowing out at 1 litre per second. Okay. Question 16. The curve C has equation y equals x squared plus 3x minus 3, and the line L has equation y minus 5x plus 4 is equal to 0. Show algebraically that C and L have exactly 1 point in common. Okay. Now, when you're finding points of intersection, then basically what you're doing is you're solving your equations simultaneously, aren't you? Okay. Now this time I've got one quadratic and I've got one linear equation. Okay. Now I'm going to take equation 2, I'm going to rearrange it so it's in the form y is equal to something. So y then is going to be equal to 5x minus 4, isn't it? Just rearranging that one. Okay, and what I'm going to do then is I'm going to substitute equation 2 into equation 1. So we're not solving by elimination this time, we're going to solve by substitution. So where I see the y in here, I'm going to write what y is equal to from the second equation. Okay, so I've got 5x minus 4 from the second equation is equal to x squared plus 3x minus 3. Okay, so you can see y has disappeared already. So just rearranging everything on one side, I'm going to get 0 is equal to x squared. Taking 5x away from both sides, I'm going to get minus 2x. Adding 4 to both sides, I'm going to get plus 1. Okay, so I've got this this formula: x squared minus 2x plus 1 is equal to 0. Okay, now if I was doing the quadratic formula for working out the roots of this, I would say that a is equal to 1 because that's the coefficient of x squared, and I would say that b was equal to minus 2 because that's the coefficient of x, and I'd say that c was 1 because that's the constant on the end. Okay, then I could put it into the formula and find the solutions, but I don't need to find them. I just need to show that there is exactly 1. So to do that, all I need to use is a bit of the quadratic formula. So if x equals minus b plus or minus the root of b squared minus 4ac all over 2a, then the only bit I really need to do this is this bit here, the bit under the square root symbol. Now we call b squared minus 4ac the discriminant of the quadratic. So then b squared minus 4ac in this case is going to be negative 2 squared minus 4 lots of 1 lots of c, which is also 1. So that's going to give me 4 minus 4 then, isn't it, which is equal to 0. Okay, and because the discriminant is equal to 0, it means that you'd be adding and subtracting 0 to minus b, so you're only going to get one solution. Normally the two solutions come from the fact that you're adding that bit under the bracket and then you're subtracting that bit under the bracket, and therefore you get two solutions. But because that bit under the bracket is 0, adding 0 and subtracting 0 give you the same value, don't they? In other words, there is only one solution. Only one solution. Which implies only one point of intersection. Okay. Now, like I say, you could go away and find, actually found the points, but you don't need to. Question 17. X is directly proportional to the square of y. Y is directly proportional to the cube of z. Z equals 2 when x equals 32. Find a formula for x in terms of z. Okay. So let's start at the top. X is directly proportional to the square of y. So I can write that down mathematically as x is proportional to the square of y. So x little fishy y squared. I can then replace that little fishy symbol with equals k. So I get x equals k lots of y squared. Okay, does that help me? No, not yet. And then I've got y is directly proportional to the cube of z. So y equal fishy cube of z, z cubed. So then I can replace the little fishy sign with equals k, but it might not be the same k. So I'm going to call it equals k2 lots of z cubed, just to distinguish it from the other k that I've already used. Okay, maybe I'll call that one k1. So I've got k1 and k2. Okay, so then what can I do? Well, I suppose what I could do is I could sub x into, well, y into x. So where I see the y there, I can write what y is worth from here, can't I? So let's call this equation 1 and equation 2. And I'm going to substitute equation 2 into equation 1. And that's going to give me x is equal to k1 lots of k2 z cubed. Okay, all squared. Okay, so this is the bit that was in equation 2, and I've subbed it inside equation 1. Okay, just multiplying out those brackets, I'm going to get x is equal to k1 k2 squared z to the power of 6. Okay, and then I've got these two values here, z2 x3, when z is equal to 2, x is equal to 32. Okay, now what I'm going to do, I think this is all, you can consider this is a bit complicated, this, but it's all just one constant, isn't it? I don't think I need to break it back down into k1s and k2s. So you've just got like a number of constants all multiplied together, which is going to give you a new super constant. So you could just replace all that with a different letter if you wanted to. I think I might just leave it in for now and just sub in all the other things. So I've got x is equal to 32, and that's equal to my k1, k2 squared, which is kind of a behemoth of a constant, times 2 to the power of 6. So what's 2 to the power of 6? Now 2 to the power of 6 is 2 times 2 times 2 times 2 times 2 times 2, so which is 2, 4, 8, 16, 32, 64, isn't it? So this becomes 64 lots of k1, k2 all squared, and that's equal to 32, isn't it? So remember, I'm treating this as all one big thing. That's like one super constant there. So then if I divide both sides then by 64, I'm left with my kind of k1, k2 all squared super constant on the right, and I've got 32 over 64, which is the same thing as a half on the left. Okay, so my k1, k2 compound constant is a half. So if you have a look up here, that x is that k1, k2 squared times z to the power of 6. So that means our x equals a half of z to the power of 6, doesn't it? Okay. Question 18. OABC is a trapezium. O to A is A to B is B, and O to C is 3 lots of B. D is the point on OB such that OD to DB is in the ratio of 2 to 3, and E is a point on BC such that BE to EC is in the ratio of 1 to 4. Work out the vector D to E in terms of A and B. Give your answer in its simplest form. Okay, so I was just checking as I was reading through that. All of that is already on the diagram, isn't it? You've got O to A being A to B being B, and O to C equals 3B. That's all on the diagram. Now, the other bits, the ratio is not, though. So O to D and D to B in the ratio of 2 to 3. Where is O to D? So O to D is there, and D to B, well, it's just a continuation, isn't it, to there. That is in the ratio of 2 to 3. Okay, so I don't know how long O to D is, but if you divide it by 2 and times it by 3, you would get D to B. And then B to E to C is in a ratio of 1 to 4. Where's B to E? So B to E to C, that is in the ratio of 1 to 4. Okay? I'm sure that's going to be very helpful. Work out the vector D to E in terms of A and B. So where is D to E? So I need to work out this vector. Okay. So we need to go via vectors that we know. And we don't know anything about anything on O, D, and B, and B, E, and C. So we're going to have to go around the other ways. So what I think I'm going to do is I'm going to say, well, I've got this point here, O, and this point up here, B. Okay. Now I can get from O to B along routes that I know about. I can go via A, can't I? So I can go around that way. So I can go from O to A, and then from A to B. O to A we know is A to B we know is B, so O to B must be A plus B. I just want to express B to C as a vector. Now I can get all the way around from B to C as well via lines I know about. I can go back this way, down here and along here, can't I? Okay, so what's that then? That is B to C. I can say I go from B to A, then A to O, and then from O to C, can't I? That will take me there. So B to A, that's minus B. A to O, that's minus A. And O to C is 3B. So collecting like terms, that is 2B minus A then, isn't it? Okay. So I've got O to B, which is A plus B, and I've got B to C, which is 2B minus A. Okay, now we want to go from D to E. That's the vector we're actually trying to find. Now, if you look at it, d to e is a fraction of O to B, which I know, plus a fraction of B to C, which I know. So I'm going to go from D to B, then I'm going to go from B to E, using fractions of those two vectors just found, using the ratios that we've got there. So I can say then that if I want to go from D to E, that is the same thing as going from D to B and then going from B to E. Okay, but D to B is a fraction of O to B, isn't it? What fraction is it? So I can see from the ratio that O to D is 2 and D to B is 3. So altogether that's 5 parts, and the D to B parts is 3 of those 5 parts. So D to B is 3/5 of O to B. So D to B is 3/5 of O to B. Similar reasoning from B to E. We can see B to E is a fraction of B to C. It's in the ratio of 1 to 4. So if you add those together, you can see that B to C is made up of 5 parts, and the B to E part is one of those 5 parts. So B to E is 1/5 of B to C. Okay, so what have we got then? Running out of space. I might need to push this up a little bit, give myself a bit more room. So 3/5 of O to B, that's 3/5 of A plus B, plus 1/5 of B to C, which is 2B minus A. Okay, so multiplying out the brackets, that is 3/5 of A plus 3/5 of B plus 2/5 of B minus 1/5 of A. I think you're going to have to budge up a little bit more. And that is equal to, well, let's collect like terms. I've got terms in A. I've got 3/5 of A minus 1/5 of A. So that is 2/5 of A. And then I've got 3/5 of B plus 2/5 of B. So that makes 5/5 of B, or just simply B. Okay, so I've got 2/5 of A plus B. That's it. That's my vector. Does it get any more simple than that? Don't think so. I think that's going to do. Question 19. At the start of year n, the number of animals in a population is Pn. At the start of the following year, the number of animals in the population is Pn plus 1, where Pn plus 1 is k lots of Pn. At the start of 2017, the number of animals in the population was 4,000. At the start of 2019, the number of animals in the population is 3,610. Find the value of constant k. Okay. So what we've got here is a term-to-term rule. Pn plus 1, the next term in the sequence, Pn plus 1, the next term in the sequence is k lots of P to n, the k lot times the last number in the sequence. In other words, you're getting the next term in the sequence by multiplying the previous one by k. Now this is actually a geometric progression if you think about it, because we're getting the next term in the sequence each time by multiplying the previous term by a constant ratio. Okay, and that constant ratio is k. Okay, so at the start of 2017, the number of animals in the population is 4,000. So if we consider this to be the first term in our sequence, 4,000, that's our, if we know it's a geometric progression, then we could call that one A, and then we're going to have our next term, which is a k, which we don't know. That's 2000, so that's 2017. That would be 2018. So 2019 would be ak squared then, wouldn't it? Okay, and that is equal to 3,610. So I know A is 4,000. I know ak squared is 3,610. So if I take AK squared and I divide it by A, I should get K squared, shouldn't I? So AK squared is 3610. A is 4000. So divide that by that. I'm left with K squared. So what's that? I'm just going to tap it into my calculator, see if it can simplify that fraction a little bit for me. Well, a little bit. That's 361 over 400. I was hoping it might cancel it down a little bit more than that. I think I could have managed to scratch a zero off myself. Calculator, thank you very much. So then K then is going to be the root of that, isn't it? So if I can root that, 361 over 400. What's the square root of that? I can see the bottom square root's to 20. I don't know about the top one. Oh, 19. So that's 19/20ths. Okay, so K is 19/20ths, so that's my constant. Question 20. Pat throws a fair coin n times. Find an expression in terms of n for the probability that Pat gets at least one head and at least one tail. Right, now we don't know how many times we're throwing this coin, so it seems illogical to be looking at all the possibilities. I think we want to try and narrow this down. So basically, the ones we don't want is to get all tails, or we don't want to get all heads. It's all the other options, isn't it? So the probability of getting at least one head and tails is going to be all of the outcomes 1 minus the probability of getting all heads minus the probability of getting all tails, isn't it? Does that make sense? Okay, because if you've got all heads, you don't have at least one tail, and if you've got all tails, you don't have at least one heads. Okay, they're the only outcomes that we really don't want. All the other ones will be at least one head and one tails, and I don't know how many heads or tails, doesn't really matter. At least there's one of them, so that's all fine. Okay, so what's the probability then of getting all heads? It's a fair coin, so the probability of getting heads is half, isn't it? So if you're throwing a coin and the probability of getting a heads is half, and you want to get all heads, then that's half to the power of n, isn't it? However many rolls you're going to do. Okay, so the probability of getting all heads is a half raised to the power of the number of throws you've got, which is n, and then we're going to be minusing also the probability of getting all tails, which spookily is the same thing, isn't it? Because you've got a half chance of getting tails one time, and then if you want all tails, it's going to be half to the power of n. Okay, so then grouping those together, that's 1 minus 2 lots of a half to the power of n. So I found an expression in terms of n for the probability that Pat gets at least one head and one tail. Question 21. Here is a speed time graph showing the speed in meters per second of an object t seconds after it started to move from rest. So we've got time along the bottom going from 0 up to 5, and we've got speed in meters per second topping out at 8 meters per second. Using 3 trapeziums of equal width, find an estimate for the area under the graph between t is equal to 1 and t is equal to 4. Okay, so we need to find the area between here and here, don't we? Okay, and we need to break it into 3 trapeziums. So I'm guessing we do it here, 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 and here. Now there is actually something called the trapezium rule that you learn at A level, which is pretty much this technique, but I'm assuming you don't know the trapezium rule formula because you're in year 11, you're a GCSE student. So what we're going to do is just going to find the area of the 3 trapeziums, and we're going to add them together, old school style. Okay, so in order to work it out, we're going to have to know this height, this height, this height, and this height. so that we can work out the sides of the various trapezium. So that one's easy enough to read. That one's a 4, isn't it? So that side is a height 4. This one is a height 6. This one, what's that? 7 and a bit? 7.2? 7.2. And then this one is 7.8. Okay. So we've got 3 trapezium. The area of a trapezium is a half A plus B H, isn't it? Okay. The 2 parallel sides added together, halved, and then multiplied by the distance between them. Okay. Now for each of these, H is 1, isn't it? 1, 1, 1, 1. That's H because they're lying on their sides. So each one of these has a height of 1. So we know H for all of these is the same. H, H, and H. They're all the same. So we're just going to find 3 areas. I'm going to do area 1. Let's do area 1, area 2, area 3. And then we're going to add those areas together. So for area 1, I've got half A plus B, where A is 4 and B is 6, times H, which is 1. What's that then? 4 plus 6 is 10, times 1 is 10, divided by 2 is 5. So that's 5. A2 is half of 6 plus 7.2 times 1. What's that? 6 plus 7.2 divided by 2. That's 13.2 divided by 2. 6.6. 6.6. And then I've got A3, which is a half of 7.2 plus 7.8 times by 1, which is, well, 7.2 and 7.8 is 15. 15 divided by 2, that is 7.5. Okay? So the area under the curve then is going to be equal to A1 plus A2 plus A3, which is 5 plus 6.6 plus 7.5. I'll just move that down a little bit. Which comes to, what does that come to? Feeling lazy. Type it into the calculator. 5 plus 6.6 plus 7.5. That comes to 19.1. Okay. Now, what does this area represent? Well, the area under a speed time graph is distance, isn't it? So it represents distance traveled. So presumably that 19.1, because I had speed in meters per second and time in seconds, so I'm assuming then that's 19.1 meters that the object traveled then during the course of the time between 1 and 4 seconds. Okay. Question 22, show that that horrible looking fraction divided by that other horrible looking fraction can be written in the lovely form 1 over x plus r, where r is an integer. Okay, so we've got to do some work with algebraic fractions here. Now, when you're dividing a fraction by another fraction, have you heard of like the KCF thing, keep, change, flip? So you keep the first one the same, you change the division sign to a multiply, and you flip the second one over. So we can say straight away then that this is the same thing as 6x cubed over 9x squared minus 144 times by 3 over x minus 4 all over 2x to the power of 4. Okay? So now I'm going to be looking for things that I can cancel, because it's always good to cancel things before you actually multiply. I can see a 2 down there that I can cancel with a 6 up here, giving me 3 and 1. I can see x cubed up here that I can cancel with an x to the 4 here, leaving me with just x to the power 1, or just a single power of x. I think that will do for now. Okay, so then multiplying those two things together, top with top, bottom with bottom, I'm going to have three lots of x minus 4, and that's going to give me 9x minus 4 then on the top, isn't it? Okay, and on the bottom, so everything went away apart from 1x, so that's going to be x lots of 9x squared minus 144. Okay, so we're looking pretty good. Right, now, just this bit here caught my eye. This looks like the difference of two squares to me, isn't it? 9x squared is a square, 144 is a square. So that means I can rewrite that bit on the bottom as two brackets. Okay, like this. Square root of 9x squared is 3x. So I'm going to have 3x and 3x. Square root of 144 is 12. So I'm going to have plus 12 and minus 12. But also 3x and 12 have got a 3 in common, so I could factorize out 3 out of 3x plus 12, and of course because I've got 3x minus 12, I can factorize 3 out of that as well. So taking the 3 out and the 3 out, 3 times 3 is 9, I can rewrite this as 9x minus 4 over 9x lots of x plus 4 x minus 4. Hope that made sense. I took 3 out of 3x plus 12 and put it at the front, and then I took 3 out of 3x minus 12 and I put it to the front, but then I multiplied my 3 and 3 together to get 9. Okay, so now I can see some more things top and bottom that I can cancel. I can cancel the 9 and the 9. I can cancel the x minus 4 with the x minus 4. So that leaves me with 1 over x plus 4. Now I'm hoping that's in the form that they want it to be. Oh, look, it is. I've got a 1 where I'm meant to have a 1. I've got an x where I'm meant to have an x, and another x there where I'm meant to have an x, and I've got this number on the end. Here, look. So it's all good. It's 1 over x plus 4. Question 23. ABC is a triangle. D is a point on BC such that angle BAD equals angle DAC, which is equal to x. They've both been marked on there already. Look, you've got one there and you've got one there. So that's been done. Prove that AB over BD is equal to AC over DC. Prove that AB over BD, where's AB? Prove that AB divided by BD is equal to AC divided by DC. Okay, is it? Let's find out. How are we going to do that? Now, really for me, I had to pause the video and think about this one. It's a bit of a toughie. Now, there is a more elegant solution to this problem, but I think most GCSE students would overlook it because it involves a little bit of angle manipulation that would probably go over most students' heads, to be fair. I'm gonna do it just using the sine rule 3 times first, and then I'm going to show you an alternative solution that uses this angle manipulation idea, which I think some of you might appreciate. It's certainly shorter than the initial method that I'm going to show you, but like I say, my honest opinion is that most students would have overlooked it in the exam. So hold on to your hats, because we're going to do the sine rule 3 times over in order to crack this baby. Right, then let's start with triangle ABD to start with. In triangle ABD, can you see triangle ABD? It's this one inside this triangle here. Okay, so we're going to apply the sine rule here. So the sine rule says A over sine A equals B over sine B is equal to C over sine C. Okay, so basically the side over its opposite sine angle is equal to a side over its opposite sine angle, isn't it? So I can use that to say that my side BD over the sine of the angle opposite it, which is x in this case, so BD over sine x is equal to AD over sine B. Okay, so the reason I picked this one out is because this side here is shared. AD is shared between the two triangles. Okay, So I'm interested in finding AD in two different ways. Okay. Actually, I could then rearrange this to get AD in terms of the other things. So cross multiplying the sine B, that tells me that AD is equal to BD sine B over sine X. Okay? Right, so that I'm done with triangle ABC now, ABD now. Let's switch. Let's look at a different triangle. Let's look instead at this triangle here, this side of the triangle. Again, I'm going to use the sine rule, and I'm going to make sure I use the sine AD because that's the one I have in common. So I can say that in triangle ADC, then what have we got? CD over sine X is equal to AD over sine C. Okay? So again, I'm going to rearrange that to make it in terms of AD, because that's the thing they have in common, isn't it? So AD then, cross multiplying that sine C underneath the AD, that tells me that AD is equal to CD sine C over sine X. Okay? Now, you might have noticed I've now found AD in two different ways from two different triangles, but they're the same AD because they're shared between those two triangles. So that means I can stick those together, can't I? If AD is equal to BD sine B over sine X and AD is equal to CD sine C over sine X, then those two things must be the same. Okay, so bringing those together, then I can say that then AD is equal to BD sine B over sine X, but it's also equal to CD sine C over sine X. Okay, so hopefully that makes sense. I'm actually going to leave the AD bit out because I'm just going to say that those two parts are equal to each other. Okay, so you might notice that they share a sine X on the bottom, so multiplying both sides through by sine X, they're actually going to disappear, those two things. They cancel each other out. So I'm left with BD sine B is equal to CD sine C. Now I'm going to rearrange that. I'm going to rearrange it so I've got the sines on one side and the sides on the other. So I'm going to say that sine B over sine C is equal to CD over BD. Okay, and I'm just going to leave it there for now. I'm just going to let that hang for a bit, and I'm going to look at the third triangle that I can look at. Okay, so now I'm going to switch, and I'm going to say in triangle, which other triangle can I use? I can use the whole thing. I can use the whole thing. So I'm looking at triangle ABC now. In triangle ABC. Okay, so what can I do in triangle ABC? I can say that AB over sine C is equal to AC over sine B. Okay, now the reason I wanted that is because I had sine B over sine C in the other one. So if I rearrange this, cross multiply, basically just switch these two around, okay, I'm going to get sine B, therefore sine B over sine C is equal to AC over AB. Okay, so notice over here, look, I had sine B over sine C, and now I've got sine B over sine C over here as well. So I can then bring those two things together. So if I call this one equation 1 and this one equation 2, I can say substitute in equation 2 into equation 1, we're going to get AC over AB is equal to CD over BD. Now it's not quite what I wanted. Can you see? But it's got all the right bits. Okay, now this one has got AB on the top, and currently my AB is on the bottom. So I want to cross multiply that over to the other side, but also I've got DC on the top where it needs to be on the bottom. So I'm just going to cross multiply those two. Okay, I'm going to switch these two around, and I'm going to say then that AC over, well, I wrote CD, they've got DC in there, so I'm just going to rewrite those letters as DC rather than CD. Doesn't matter which way around I write them, and that is equal to AB over BD. Okay, and that's what we've got over here. AB over BD is equal to AC over DC. Okay, so that was fairly hideous, but we kind of got there in the end. I mean, maybe I'll just divide this up so it's a little bit kind of clearer to understand. So I kind of did this step first, then I did this step, then I did this step, then I did this step, and then I did this step. Okay, so yes, it was long and it involved the sine rules in 3 different ways, but finally what we wanted dropped out the other side, so I'm happy. Okay, so if you didn't like the 3 times sine rule way, this is the alternative solution then. So I'm going to go run through the same problem again, but doing it a slightly different way. Now this method involves kind of the relationship between this angle and this angle, and in particular the sine of those 2 angles. We'll come back and look at that in a minute. So if you remember, we were looking at the ratio of AB over BD, which is this side over this side, compared to AC over DC, which is this side over this side. Okay, now you might notice that one of those sides is opposite the given angle there, and so is this one. This one is also opposite the given angle there. Okay, and the other side is opposite this angle down here, D, and the other one is opposite this side of angle D. Now there are different angles, okay, but they're kind of related to each other because they lie on a straight line, don't they? Okay, now if we use the sine rule in triangle ABD first. So again, in triangle ABD, I'm going to use the sine rule for those 2 sides that we want to find, AB and BD. Okay, so side AB over the angle, what's the angle? This one here, isn't it? I'm going to call it D dash. Okay, so AB over the sine of D dash is equal to the other side, BD over the sine of X. Okay, then I'm going to rearrange that so I've got, so it's in the form of what's on the left there, AB over BD. Okay, so I can do that by cross multiplying these 2 things. Okay, so moving one up and moving one down. So I'm going to get AB over BD is equal to sine D dash over sine X. Okay, so that's in triangle ABD. Now let's switch to the other triangle, triangle ACD. So in triangle ACD. Okay, now I'm going to do the same thing. I'm going to use the sine rule to find with those 2 green lines there. So first off, I've got the one opposite angle D, which this time I'm going to call D double dash, just to distinguish it between the littler version of angle D. Okay, so the side AC over the sine of D dash dash double dash, that is equal to my other side, DC over sine of X. Okay, right, so again I'm going to make it look like this bit over here, AC over DC, by cross multiplying these two things again. I'm going to move that up there, and I'm going to move one down there. Okay, and then it will look like this thing on the left here. Okay, so let's do that. So then AC over DC is equal to sine d double dash over sine x. Okay, so note that we've got the bit on the left of what we want to find up here and the bit on the right of what we want to find down here. And also notice what we've got over here. We've got sine x and sine x that are the same, and we've got sine d dash and sine d double dash, which are not the same because they are different angles. Or are they? Now, if you get your calculator out, let's say d dash, I don't know what d dash is, but let's say d dash was 30. Then d double dash would be 180 minus 30, wouldn't it? It'd be because they're lying on a straight line, and so that would be 150, wouldn't it? Now, if I worked out what the sine of 30 was, sine 30, just tap it into your calculator. Sine 30 equals, well, you should know that anyway because it's one of the given angles. It is a half, isn't it? So the sine of 30 is a half. But maybe you don't know what the sine of 150 is. So if I type in sine 150, you'll see that's also a half. So those two sines are actually equal to each other. So the sine of 150 is also a half. So the sine of 30 is the same thing as the sine of 150. Now, is that a coincidence because I happen to pick 30? Now, you can actually try this with any angle. If you make angle d dash any size and then make d double dash 180 minus that side, you'll find that you always get the same sign when you take the sign of those numbers. And the reason for that is, if you look at the graph of sine x, okay, sine x is a nice sine curve, isn't it? It goes up, goes down, goes up again. Okay, so that's in 360 degrees, isn't it? So that's 0, that's 180, that's 360, in the middle there, that's 90, and that is 270, isn't it? Okay, now if you pick any number on our scale here on the left hand side for the sine of x and read across to your curve, you'll find that you get one solution down here and a kind of a matching another second solution over here, and these two numbers are always related to each other. If you can see that this curve has got a line of symmetry passing through 90. Okay, so whatever this angle is on the left, let's say it is alpha, then this angle on the right is going to necessarily be 180 minus alpha. Okay, so the sine of alpha and the sine of 180 minus alpha always give you the same answer. Okay, and because as angle D plus D double dash is equal to 180, then the sine of D dash is equal to the sine of D double dash. Okay, this is always the case. Okay, just necessarily because of the way that sine works, which means that these two expressions here, this one and this one, are actually identical, aren't they? So if these two things are equal, then these two things here must also be equal because they're equal to each other, aren't they? Okay, so then I can say, therefore, AB over BD is equal to AC over DC as required. Okay, now like I say, I don't know how many students would actually have spotted this rule here. It's a little bit off-piste if you ask me. I think it's a little bit cheeky actually to have this in the exam. I think if you were doing further maths GCSE, you're more likely to know that and spot it, but you'd be forgiven not to know it in the exam, I think. So I've given you two different alternative ways of solving this problem, one with and one without that little extra piece of info. So anyway, you can decide which way you'd prefer to tackle this problem. You can find more exam question compilations over here. For more past paper walkthroughs, click down here. If you want to visit my Amazon shop with my recommendations for calculators, revision guides and other maths related stuff, click down here. Good luck in your revision and in your exams, and see you again.